So this is the classic kind of dative-donor interaction that you're all familiar with. You take the HOMO of carbon monoxide, which is a lone pair on carbon, you donate it into a vacant orbital on the metal. Now, if this metal was a classic octahedral metal like chromium hexacarbonyl, so in chromium hexacarbonyl, what metal d orbital is drawn there? It's going to be one of the EG set, because it's the EG set that point along the axis. It's dx squared minus y squared. This can only be one d orbital, dx squared minus y squared, pointing along the x and the y axes, because that's the directions that an octahedron of ligands are coming in on. So we must have our carbonyl ligand coming in, or at least this one, there'll be 6 of them. This one is coming along either the x or the y-axis. So we have a lone pair donated into an unoccupied orbital on the transition metal center. Now, what shape is the LUMO? Well, the LUMO is the pi star orbital, or one of them. They're 2 degenerate pi star orbitals. Those pi star orbitals will have this shape. Okay, so they will have a shape where essentially you have an antibonding orbital, so you have lobes of the same phase diagonally opposite one another here. So this is an antibonding orbital. It's antibonding with respect to the carbon-oxygen bond, meaning if we occupy it, we will weaken the carbon-oxygen bond. Now, if you look at the symmetry of that, this has the same has the right symmetry to overlap with orbitals. So if this is the same xy plane, this d orbital, if this is the xy plane, which d orbital is that? So this is dxy. Now dxy doesn't point along the axis, it points between the axes. So if this is pointing between the axes and these lobes are pointing between the axes, they have the right symmetry to overlap with constructive phase, so they can form a new molecular orbital. And in this case, of course, these are the T2G orbitals. And these two T2G orbitals are occupied. They are occupied with electrons. However, the pi star bond, the pi star orbital is not occupied with electron density. So this is what's special about carbon monoxide ligands. Carbon monoxide ligands can accept electron density from the transition metal to the pi star orbitals. And that's what's meant by a pi acceptor ligand, or sometimes called a pi acid. So this is what's unusual. Normally you consider a ligand to be donating electron density from the ligand to the transition metal. If you have a pi acceptor ligand, it's accepting electron density from the transition metal into its pi star orbitals, into its anti-bonding orbitals, and that has the effect of weakening the carbon-oxygen bond. So this is a bonding contribution with respect to metal-carbon. So it's bonding with respect to metal-carbon. This is bonding with respect to metal-carbon, but anti-bonding with respect to the carbon-oxygen bond. And that's going to be really important in a minute when we look at the infrared stretching frequencies of metal-carbonyl complexes. The one point I didn't stress here, this process of donating electron density from the metal to the ligand is known as back bonding. Okay, so classically bonding is electron density from the ligand to the metal. Back bonding is electron density from the metal to the ligand. If we look at carbon monoxide is a polar molecule. Okay, it's a polar molecule which normally has, at least to begin with, a carbon-oxygen triple bond. So it's a very strong carbon-oxygen triple bond, and it has a distinctive stretching frequency. And the beautiful thing about carbon monoxide is it comes around 2,000, plus or minus a bit, but around 2,000 wave numbers. And nothing else comes around 2,000 wave numbers. So it's ideal for doing infrared spectroscopy because it doesn't overlap with any of the other complex regions of the spectrum. So carbon monoxide is a great chromophore in infrared spectroscopy. Now, what we find is that in neutral complexes, so imagine your compound is neutral, then you can tell whether or not your carbon monoxide ligand is bridging or terminal based on its stretching frequency.